And where? Which?
Number 9.
Okay. All right. Let's take the equation for free fall on Mars. The position of whatever is in free fall is equal to that on Mars. Okay? How long does it take a rock falling from rest to reach a velocity of that? Well, what is velocity relative to position?
Is there a formula you're talking about?
Well, there is kinda. The formula being that whenever you're not sure what to do, take the first derivative.
Okay.
Okay, and that's the truth. So the first derivative is velocity. In other words, position and then velocity is the first derivative of position, and the first derivative of velocity is acceleration, which is the second derivative of position.
Okay.
So S prime would be 3.72 t. And S prime is velocity. So velocity as a function of t is equal to that. Okay? Now you can answer the question, how long does it take a rock falling to reach a velocity of 27.8? Well, how do I solve that? If I want to know where velocity is 27.8,
Would I put that in for t?
for v of t, not t. 27.8 is the velocity, and when does that occur? At what t?
So would I divide by that?
Okay, what do you get? That's your answer.
Okay, 1 second, putting in the calculator.
Yeah.
Nice.
And that's the time on Mars.
7.47. Yeah, you got 7.47.
Seconds on Mars.
Correct.
Okay. On the other planet, it has a different position function. It has a position function on Jupiter that is 11.44 t squared. Now, hold on a minute. 11.44 t squared. So what is the velocity function on Jupiter?
That would be, so 2 times 11.44. 88 t.
Okay. And again, they want to know where on Jupiter does it hit a velocity of 27.8?
So when I divide both sides,
You should get
so
1 and change.
27.8 divided by 22.88. That'd be 1.215, or if I round it, 1.22.
Okay. Now, what does that tell you about the difference between Mars and Jupiter? On Mars, it took 7.47 seconds to reach that velocity. On Jupiter, it only took 1.22 seconds.
So gravity's less.
Gravity's greater on Jupiter, a lot greater.
Okay.
The reason it is because it's bigger. Jupiter is gigantic compared to Mars.
Correct.
So gravity being greater on Jupiter means that this particle or whatever it is that was dropped from a certain position reaches that velocity much quicker because it's accelerating much quicker.
Okay.
What next?
Next I'd like to do one on the other email I sent you.
Okay.
That'll be number 12.
Oh, a speeding bullet.
Yep.
Faster than a speeding bullet. Must be Superman somewhere in here. All right, let's see. So here, notice that position is almost always given as S. And when I say position, I mean where is this thing relative to the surface of the planet? In this case, we're on the moon. We're shooting a bullet straight up. Its position after t seconds is given by this. So let's just analyze this function for a moment. Where is the bullet at time 0?
So I put 0 in for all the t's.
So what's its position?
I believe s equals 0.
Correct. And s being the height. Notice that it would reach a height of s. So here's the thing with calculus. You're either going straight up and down, like that, along the y-axis, or you'll notice a lot of problems have particles moving along the x-axis, like that. And that's the nature of this level of calculus, is you're either going to be going straight up and down or you're going to be going left and right. You're not going to be going slanted and you're not going to be going curved like that. At least not yet. You might get to curved because that's projectile motion. But in all of these problems that we're looking at, you're either going straight up and down or you're a particle moving along the x-axis, like number 7.
Okay.
Number 7 is just a particle moving back and forth across some horizontal axis. Well, number 12 is a particle, in this case a bullet, moving up and then back down again.
All right.
Now, on Earth, they tell you that this is its height function. And the difference is that Earth's heavier than the moon, bigger, so it's got greater acceleration. When you're looking for the acceleration factor, that's what that number is right there. Okay?
Okay.
On Earth, it's much greater than the moon, about 6 times greater. We know that gravity is about 6 times greater on the Earth. Now, when they say in the absence of air, they mean that. In other words, on the moon, there is no air. So on the Earth, this would not be exactly true with the presence of an atmosphere. But if you remove the air, this formula here is the one to go with.
Okay.
How long will a bullet be aloft in each case? Well, T equals 0 is the moment you fire the gun.
Okay.
When does the bullet come back to Earth?
Back at 0.
So on the moon, I'm going to set its height equal to 0. And that should actually yield two solutions. In other words, it should tell me when the bullet was fired, because its height was 0, and when it returns to Earth. Well, I can factor a t out of both of those. So there's the 0 answer we're looking for. We know that when, in other words, the solution to this equation is when this is 0 or that's 0, right?
Yep.
Well, the first one is 0 at the beginning. In other words, when t equals 0, the height of this bullet is 0. But the second one, well, now I got to set that equal to 0, which means 2.6t is equal to 832, and t equals 832 divided by 2.6. What time is that?
That would be, 1 second. 832 over 2.6. That is 320.
So 320 seconds is how long it would take for the bullet on the moon to come back to the moon.
Okay.
Now let's take the Earth. We're dealing with a different equation. So in this case, notice that this is not a calculus problem. This is strictly an algebra problem. So I'm still going to set the height to be that, and I'm still going to factor out a t, and that still produces the first 0, but the second 0 comes when 832 is equal to 16t, t is equal to 832 divided by 16. What's that number?
That will be 52.
Seconds.
Correct.
And that makes sense. If you were to fire the exact same gun on the moon, you would expect it to stay up in the air a lot longer, because gravity is less, so it's going to go up higher. That's
going to take longer.
right, and the force of acceleration from gravity is less, and that's the main difference in these two things.
Okay.
How long will the bullet be aloft? We just figured it out. How high will the bullet go in both cases? This is a well, it's not really a calculus problem. I mean, it is, kind of. Probably the easiest way to solve it is with calculus.
Okay.
There's my two positioning functions for the moon and for Earth. How do I figure out where the peak of that thing is? It's traveling like that, a parabola, in both cases, right?
Correct.
Well, there's its peak. How do I find the vertex of a parabola?
Does that have anything to do with like tangent?
Well, there's two ways. As I said, when you're looking at quadratics, if you only have to find the vertex, that's an algebra problem. That's not a calculus problem. But in this case, it's actually a fairly difficult algebra problem. In other words, we've got to find the vertex, so we got to do minus b over 2a, or I got to put this thing in vertex format. In other words, there's a lot of things I got to do to find the vertex. Actually, a much easier way using calculus to figure this out. What is the velocity when it reaches the top?
0.
So let's do this.
Oh, we put 0 in.
Well, first of all, we got to take the first derivative. What is velocity as a function of time for the moon?
I believe for the first one will be like 832 minus, 2.6 times 2. 5.2. Okay, negative 5.22.
And we know there's only one place on the path of that bullet where the velocity is 0.
And that's the top.
And that's the top. So you get t equals 832 divided by 5.2, which is what?
That will be 160.
After 160 seconds, the bullet is at the peak. And if I do the same thing to the Earth, in other words, if I want to find its velocity function, it's 832 minus 32t, set that equal to 0, and you get t equals 832 divided by 32, which is like 25 seconds, something like that.
26. Super close.
26 seconds.
Yep, you're close.
And again, you are looking at it, the things make sense. In other words, I know the bullet's going to go a lot higher on the moon because the gravity is only 1/6. So it's going to take longer to reach its top. It takes 160 seconds. Only takes 26 seconds on Earth. And again, notice that that's a factor of about 5, maybe, or 6 really. It's perfect 6. So everything we're coming up with here, the moon is 6 times longer in the air than the Earth. The moon's peak is 6 times higher than it is on the Earth. And we know that the moon's gravity, or the Earth's gravity, is 6 times that of the moon. So that's not accidental. All of that is as it's supposed to be. In other words, if we were dealing with a planet that had gravity 10 times greater than Earth, then it would only stay up in the air for 16, or excuse me, whatever the solution to that one was. Let's see, it would reach its peak at 2.6 seconds instead of 26 seconds.
Okay.
All right. So it all has to do with gravity, and gravity is what determines both of these position functions. It's because of gravity. That 16 is not accidental. You will see that 16 a lot if you take any courses in physics. In other words, on Earth, a falling object has a formula that has a 16 in front of the t squared always. In fact, a minus 16. Because the gravity on Earth is 32 feet per second, and that translates to a coefficient there of 16. All right, what else? We got like 6 minutes.
We can do the next one as well.
Okay.
Or start on it at least.
Okay. Again, these are vertical. Vertical is a little different than horizontal because vertical always has gravity affecting it. Whereas a particle moving along the x-axis is just moving back and forth, so gravity isn't part of it. But the key thing on number 13 is this function right here. Notice again the 16, because we're on Earth.
Okay.
What would have been the ball's velocity, speed, and acceleration at time t? So what they're saying is, what is v of t and what is a of t? And what's speed? First of all, let's do v of t.
So for v of t, first derivative.
Uh-huh.
So that would be negative 32 t.
Correct. That's the velocity function. What's the acceleration function?
What would I substitute in this case?
Just take the first derivative of v of t. In other words, acceleration is always the first derivative of velocity. Velocity is always the first derivative of position.
So negative 32.
Uh-huh. Speed is always the absolute value of velocity.
So that would be 32.
32t.
Okay.
Okay. Now, the difference between speed and velocity is a vector. It's got the same numerical value as speed, but direction is important also. And when I say minus 32 velocity, that means it's going down. If you had a velocity of plus 32, it would be going up. And in either case, speed is going to be whatever speed is. Speed is not a vector. Speed is a scalar quantity. Speed is like how long is this table? It's 24 inches. That's a scalar quantity. Vectors have not only magnitude but direction. So velocity is always going to have a direction to it, whereas speed does not. Speed is just the absolute value of velocity. Okay, how long would it take for the ball to hit the ground?
So would it be 179 divided by 32?
Well, let's go through the concept of this.
Okay.
Which function am I going to use, first of all? This is incidentally s of t. Might as well put that in there. I've got the position of the ball, the height at any point in time. I got the velocity of the ball at any point in time. And I got the acceleration of the ball at any point in time. So when they say how long would it take for the ball to hit the ground, which one do I want to use?
I'd say velocity. Or no, would it be the beginning function with s?
And sets s to be what?
That should be 32.
What's the height when it hits the ground? S is the height.
Yeah.
Okay. So I set this function equal to 0 and I solve for it. And you get 179 divided by 16, the square root of that. Because look at our position function, that's t squared. So if I want to solve for when t gives a height of 0, then I would have to take the square root of it.
Okay.
And that gives you the answer to B. Now, number C, what would have been the ball's velocity at the moment of impact? Well,
0.
No, they actually,
because it balances.
well, they kind of mean at the moment before impact.
Okay.
In other words, obviously, after impact, the velocity is 0. But right before it hits the ground, how fast is it going? Well, let's go back to the previous question and solve that. What'd you get for t? T is the square root of 179 divided by 16. What is that number?
That is 179.
Three and change.
I'm having problems with my calculator right now.
I'll do 179 divided by 16 and then take the square root of that result.
179 divided by 16.
Okay. Now,
That equals 11.18.
I'm sorry, what?
That equals 11.18 without doing the square
Take the
root.
square root of that number. It's 3 point something.
3.344
seconds. That's how long it takes that cannonball to hit the ground. Now we have a velocity function we already figured out. What's the velocity when it hits the ground?
Negative 32t.
What's the velocity when it hits the ground after 3.344 seconds?
So would I put that in for t?
Yeah. In other words,
okay.
What we want is v of 3.344 plug
negative
in
1
t. What do you get?
Negative 107 point. Oh, so just 107.
And that's feet per second. Okay.
Okay.
Notice the negative sign. That means it's going down. It's not going up.
Yeah.
So its
okay.
speed is still 107 feet per second, but its velocity is minus 107 feet per second.
Okay.
All right. So we've done 13.
Thank you. I appreciate it.
I'll let you go. That should have been helpful. Okay.
Yes, it was really helpful. I appreciate it. Thank you.
All right. Bye-bye.